Not the original one. Okay, the original one existed. I think actually owns it.
How rich is he now?
He's actually not. He left Coinings now. Well, he did it for coins, so you don't get the money.
Oh.
So you get $2, but
Now
you
it's
do.
used on every small.
Yeah.
Smartphone.
He made billions of dollars. I mean, billions of dollars. And so, but the original Gorilla Glass was done, I think, sometime during the 60s, but then they figured out how to put it into their fusion draw process, which then they dominated flat screen TV. And then John, who's an Alfred alumni, and my greatest contribution is I taught him quantum mechanics. He went and modified it to, Gorilla Glass 2, 3, 4, whatever it is. Wow. And then he.
So to do stuff like that, we need no quantum mechanics.
I mean, a lot of stuff. And quantum, and I would argue any engineer needs quantum mechanics. That's just my own personal.
Isn't Gorilla Glass the ion exchange one?
No, that is not ion exchange.
Which one is that?
Ion exchange are any of your EpiPens that you have, for allergies, they're all ion exchange.
We're like me and Ralph were working on testing the abrasion, pre-abrasion and post-abrasion effects on ion exchange. So, because if you make controlled cracks,
Yep.
ion exchange would go into the cracks, the solution, and that would strengthen the stuff. And we're trying to see if there's any difference after you post-abrade it, because every time like glass comes out, you post-abrade it in any way, like you rub it against anything. Does the pre-abrasion make glass after ion exchange stronger when it's post-abraded? So it's kind of like interesting to see the surfaces interact.
Oh, the surfaces, I mean, when you're doing ion exchange, it's all surface effect.
Yep, and we're like, with some integration methods you taught us right here, even though it's a little different, we figured out like the formula for the depth of the ion exchange due to like the mass difference, you think? Yeah.
Yep, okay.
So,
Okay, so when's our first test?
Monday.
Monday, and it's going to be during lab again. I have 2 lab sections. The first one starts at 120. You're welcome, even if you're not in the 120 section, you can start there. You can go late, that's fine. The second lab session ends officially at 5:10. If you want to stay a little bit later after that, then that's also fine as well. Okay.
Is the test in here?
The test will not be in here. It's going to be in the other little room there. I'm going to see if I can actually get into a different room, because basically that could be a little cramped if everyone shows up at the same time, which is fine if they do. But we'll come up with something that works. Okay. We'll have some people on the floor. Some people will hoist from the ceiling. Okay, we'll come up with something.
We can do it on.
Yeah, no, we'll have a lot of different places for people. Okay. There's a little sink. We can put people in the sink. What? Sure. Okay.
All right.
We'll hoist up. We press into place.
All
Okay.
right, awesome.
Okay. So
I can look at everyone.
we're going to continue to do more examples today. And what's our first our homework is due on Friday, on Monday. What is it? It's a practice test. So work on that, hand it in, and that'll be good practice for you good review for you to get ready for class. Okay. So we're looking at, and Riley, if sorry about the roads. If the recording ever goes blurry, let me know, and there's a way of fixing it, because the recording periodically does go blurry.
I think it just went blurry.
It just went blurry, really?
Yeah.
That because I moved a.
Hi, Eddie.
Okay. So we now have, if we have a point charge here, Q. If I come out from distance here, R. I now know E at this point and B at this point. What is E? E is KQ over R squared. That's the magnitude, and it is it's a vector. Okay, so that would be the electric field at this point. Now we have the voltage at this point, and this is KQ over R. And it is a scalar. Okay. And we said, suppose you have like a weird object. We did the wire last time. So if we had a finite wire, and if I want to find the voltage at this point here, what do you have to do?
You have to treat it as a collection of point charges.
You have to treat it as a collection of point charges and add everything up like this. Okay. Let's do another example of this, and then what I want to do is I want to show you. Turns out we're going to get a third way to calculate the electric field. It turns out that if you can calculate V, you can do this little calculation to it, and that'll give us E. I want to show you how that works. Okay. Let's take another example of. So this is a ring of charge. Ring of uniformly distributed charge of radius r in the xy plane. This is r. So I have positive charge all the way along here like this, all uniformly distributed. And this is going to be part A. This is Z. I want you to find Z here. I mean, find A here. Frequently called B. Okay. Find B here. Okay. You tell me how to proceed.
We treat the ring as the collection of point charges.
Yeah, we have to treat this as a collection of point charges. So we come over here. I'm going to draw, here's my little point charge here. So treat the ring as a collection of point charges. So we're going to call this, what we call this little charge here? DQ. And from here to here is R. Now, do I draw the voltage like this?
No,
How come?
it's a scalar.
It's a scalar. Do not do this. Okay. If you're doing something like this and no, stop. Don't do that at all. Okay. You do that for the electric field. Okay. What we have here. What will I draw then for that point there? I won't write V, but rather dV. Why that?
Because we're looking at
Caused by DT.
Exactly. It's a small part of the voltage. So I'm going to call it DQ. Now we only have one voltage expression. This is right here. So modify this expression here for our buddy here.
we have more than one.
K DQ.
Well, I mean, that's obvious. I mean, I would have to rederive the one for the wire.
Okay.
I mean, obvious ones.
Oh, you
But
mean,
the wire one would help.
oh, you mean the voltage at a point, not a voltage difference.
Correct.
Okay, yeah.
They're different things. So this is going to become what?
KQ.
Yes, KQ over R, but now the Q is DQ. So it's KDQ over R. Okay. Now, do I have to worry about this one over here with casting out part of the component?
No.
Good, this is nice, because this is a scalar, so these just add. Okay, so these are really, really nice to work with. So if I want the total voltage, I have to add up all the little voltages. I have to integrate this along the ring. What can I pull out of that integral?
K, R.
And if I sum up all the little DQs, what do you get?
Q.
The total charge on the ring. Now there's a little trick here. You can say, well, wait, this looks exactly like this. We haven't done anything. Tell me why we actually have. Why is this R here? Not this R here.
Because the R over there is the distance to a point, and
Yep.
that R is the radius of a disk.
No.
What? Oh, it's not.
Yeah,
Yeah,
this R here is this guy here. So this is R here. This is Z here. So this little R as well.
yeah, makes sense.
R squared plus
R squared plus D squared, square root. Okay. Whereas this, so that's gonna be the distance from here to any point along this string here like this. Okay. So if you go and put it in here like this, this DQ here is one of the little point charges here.
1.1.
Yeah, because we treated this as a whole bunch of little point charges here, a whole bunch of little DQs. Now, does that make sense? Hey, what do you think part B of this is going to be? I'm going to go to a different shape now. What do you think the shape is?
Sphere.
Disc. The sphere would be hard, especially because we couldn't treat it as,
Collection of pointers.
you can't treat it easily as a collection of rings.
Yeah.
Okay, you can, but you have to kind of, that is a little beyond the scope of this
Can
course.
you go from 0 to pi? And
You can, but we're not going to. Because that gets actually kind of hard. That starts getting, the limits get a little tricky on that
That's
part.
really weird.
Okay, yeah, so we're not gonna do that. way.
one weird thing from Calc 1.
Oh, you have to do more than one little thing from Calc 1. If you take the advanced course of this, called Advanced Electricity Magnetism, I hope you all do. One of the first things you do is you integrate over a lot of weird shapes. You go, wow, that hurt. Okay, that's part B. Modify the V ring expression for a uniformly charged disk of radius. So in this case here. So here's a disk. That's R and it's uniformly charged, so there's positive charge. So how do we do this?
We want to integrate from 0 to R the rings, but
Yeah, what are you gonna do? Why did I have you do the ring over here? You can view the disk as
collection of rings.
a collection of rings. So what we're gonna do, we're gonna view the ring, view the disk. As a collection. So we have to modify our little expression. What would be the first thing I would do?
Write an expression for it, right?
Even before you're writing an expression, always draw your picture. Okay, so I'm going to redraw this. I'm going to redraw in red. Because it starts with R,
Right.
and red starts with R. So that's why I'm doing that. It's amazing. That's a little funky. I like this slope here. Yeah, that'll work. Yeah. Okay, so, and again, this is all solid here like this. So the first thing I want to do is come over here. And I'm going to come out with some radius here. What will I call that radius?
R prime.
Okay.
I'm going to call it R prime. And then what will I do? Then I'll draw a little ring. Like this. And what will I give my little ring?
A thickness.
Yeah, I'm going to give a little thickness here. I'm going to shade it in. And what will I call the thickness of my little ring? DR prime. So what I have to do is I have to take this expression here. I have to modify this for this picture over here.
This is exactly what we did with the
Turns out it's the same. Okay, physicists, again, remember from first semester, I told you physicists are one-trick ponies. You learn a trick and you beat it to death. Again, physics is the easiest science you're going to do. People don't believe that. But I mean, again, don't believe me, go into biology. You know, you find out how some cell works. So what does a cell work? Yeah, it's like this. And what does this molecule do? It twitches. And if it doesn't twitch, you're dead. And then how do you make this thing like this, where you take this thing here and it goes into some incomprehensible device, that enzyme that does who knows what the hell to it. And then you end up with something like this. And say, see?
Yeah.
That's how it works.
Yeah.
Yeah. Okay. And then compare it to this. There's no comparison. Okay. So modify this. So I'm not going to call this V here anymore from the string. I'm going to call this dV because it's going to be a tiny part of the voltage at this point here. Now modify this expression. This Q here's the charge in the ring. What's going to be the charge in my ring here?
DQ.
I'm going to call the charge here dQ. Over.
R prime squared.
Yeah, this right here is the radius of the ring. In this case here, the radius of the ring is R prime. And this case is the same. Okay. Does that make sense?
Was that always R prime, or did you just make it R prime?
I just made this one out here R prime to not confuse it with this R over here. Okay. Does that make sense? Then if you want the total V for the disk, oh, and then take organic chemistry. Yeah, where you have this, and you're going to make this molecule over here. Right. Okay.
And the angle between them is like 109.72.
I honestly don't know how anyone gets out of organic chemistry without accidentally making a plastic explosive and blowing out the building or making nerve gas and killing everyone. I don't believe anything in that claim. Okay. I had a friend at one place I was at who was an organic chemist, and he was really proud of this female undergraduate he had because she was thinking like he did. So they had made something and it kind of reacted and kind of splurted out all over the place. And so to figure out what it was, what was she going to do? She was going to take her finger and put it in it and taste it. And that's exactly what he was going to do. And he was really proud that she had actually come to this conclusion that you're going to taste it.
But
That was like
Yeah.
the most
Okay.
ridiculous.
Yeah.
but that's like the first thing that you're told not to do. Is you don't like. Well, that's only for chemistry. Biochem is.
Okay. Or
It
some
does
of
brain
them.
damage.
Archaeology, you can lift things.
No, you can't. You
Okay,
can't.
let's keep going. What's the technical problem here?
We have two variables.
Yeah, we're integrating on Q, but the
R prime.
R prime is changing. So what do we do? What's our trick for this?
Right, sigma.
Sigma?
We introduce sigma.
Because
Sigma is
lambda, sigma, rho.
charge per unit area. And we're going to write this for this little ring here. So let's write this for the ring. So what's this? What's the charge of the ring?
DQ.
DQ. What's the area of the ring?
2 pi r dr.
Yes, the circumference 2 pi r
Prime.
times the thickness prime times the thickness dr prime. So then your DQ sigma 2 pi r prime. I haven't drawn a big arrow yet today. I'm going to put this in over here. Okay, I'm going to redraw this expression over here. I'm making just exaggerated use of the arrows. I really like them. Okay, so the three of the disk. Is this K sigma 2 pi r prime dr prime over the square root of r prime squared. Now this is all in terms of one variable. Now where do we integrate from? From where to where?
From 0 to R.
From 0 to R. That's where those rings start. They start with a radius of 0. We add them all the way up until we have a radius of big R. If I had a washer of inner radius A and outer radius B, what would you do?
A to B.
You'd integrate from A to B. Yep. Okay. So what can we pull out of that integral?
K 2 pi.
Sigma. 2 pi k sigma. Okay. How would you integrate that? Again, try to do it in your head. What would you could do use sum. Okay, so you can do use sum, but I want you to start doing use sum in your head. So what would you have to differentiate to give yourself this? Exactly, something to the 1/2 power.
Sigma root
So what would you guess to the 1/2 power?
squared plus c squared, the bottom term, but then because of the chain rule, you have to put a 1/2 out front, but then that would cancel with this.
So you'd have that. So the question is, does anything go in the
Yeah.
front?
But then that would.
So does anything else go in the front?
Yes, because you want the space.
To our prime.
No, 4. -4. Yeah, 4.
So we have a 4. That I'm hearing 4.
Nothing.
I'm hearing nothing.
There's a 2 there, but then there's. a
Here's
4.
here's a 2 there, but then there's a 4. I just reiterated people are trying.
Mhm.
Okay, why are we getting just as it is? Okay, check it. If you differentiate this, what do you have to do? What do you do with the 1/2?
Subtract 1.
You pull it out in front, and then you decrease this by 1, giving minus a half.
Yeah.
And then you have to take the derivative of the interior, giving
To our prime.
2r prime. So that 2 cancels the 2 down there and Shazam, you're done up here. That makes sense? So now if you put in the limits. Put in the limits, what do you get? You get 2 pi k sigma. Okay, the upper limit gives me square root of r squared plus c squared. Minus the lower limit gives me z squared, square root of that, so that just gets me. Does that make sense? Questions? Now I want to show you something else, okay? So it turns out, so this is now kind of theory. It turns out that a very simple way to find E is to first find V. And I want to convince you of why this is the case. So we will see. I will show you. We will prove that E and V are related by the following expression. Just so you know, okay, this is gonna, if you haven't seen this before, this is gonna look like, oh no, I'm dead. This isn't hard, it's just gonna look funny. Okay. Related by the following expression, E equals minus the gradient of V, where
That's nice.
where this is called the gradient operator. And it is defined by, okay, I hat, partial with respect to x, it's j hat, partial with respect to y, it's k hat, partial with respect to z. So it turns out this is going to be really useful. I haven't proved that. I'm going to prove that today now. Okay. Now, the reason why this is easy is, why is it easy to find V?
The scalar.
It's a scalar. So what you can do, you can find the B, because it's a scalar, a whole lot easier. Then you do this little exercise to it, taking the negative gradient, and Shazam, you get yourself an electric field.
Is there a name for that, or is it just,
Well,
is it like some sort of a law? Or
no, that's just,
technical? Okay.
no, it's just. It turns out when you take more physics, it turns out you have to add another term. This is only true electrostatics. It turns out, don't even write this. It turns out that if you take electrodynamics, you have to add another piece of this. This is called the vector potential, which is connected with magnetic fields in a really odd way. Oh, that's important. Don't worry about that. That's well beyond the scope of physics. I needed this expression on erasing. And that's what happens when you're in the science center with limited blackboard space. I'm like, oh no, it has as much blackboard space as you could possibly need. Okay, so let's do the proof of this. Okay, proof. Okay. So I want to do, this is first of all, so first. Let's look at we'll do it this way. Let's look at a 1D example. Okay. I'm going to set this up. This is kind of a warm up. So this is we'll start up. This is first. This is a warm up exercise. I want to prove the 1D example of this. So the 1D version. This is, what do you think the one, first of all, it's one dimensional, what does it mean? It's only depending on X.
Yeah.
Okay. So the 1D version of this is going to be the X component, I'll just call E here. It's going to equal to minus, just going to be that. Okay.
Yeah.
That'll be the 1D version. Let me do the proof of this. Okay. I did define a voltage difference. Okay, well, it's delta U over Q. But we also know we can write that as
Negative integral of electric field by dl. Beginning to end.
okay. Okay. So let's actually kind of draw this out. Now we're in one dimension. So here's your initial spot. Here's your final spot. If I'm in one dimension, what does my path look like?
A line.
A line. Like that. So here's my DL. And here would be my X, here would be my E, because I'm just in one dimension. Well, what would that magnitude of DL become?
dx.
It just becomes DX, because I'm just in one dimension. So that would be DX. In this case here, this would give you this minus integral E dot DL cosine of 0. This shows the initial to final spot. Cosine of 0 is 1, and DL becomes DX. So this would give you minus this magnitude of E, okay, DX from some initial to final spot. Now, how do you define a delta?
Final versus initial.
Final minus initial. So I'm going to call this initial. I'm going to call this initial spot here X naught. What do you think I'll call the final spot? I'm just going to call it X. So let's give me delta V equals V at X minus V at X naught equals this minus integral from X naught to X, this magnitude of V dx. Okay, right, this is just nothing but really just dx. Okay, what's the fundamental theorem of calculus? Don't get to use it a whole lot.
Yeah, it's gonna be the integral that definite integral equals change in the. I don't even know how to say it. I can write it to you. But
If you differentiate both sides with respect to x, what happens?
you get
What does the derivative do to the integral? It gets rid of it. Okay. So if we differentiate both sides here, the derivative of this from here is just dv dx. What's the derivative of a function evaluated at a particular value?
Zero, since it's a constant.
Yeah, this is a constant here. So that gives me 0 equals minus. Then if I take the derivative of this, I just really get this function here evaluated at that point here. So this gives me this magnitude d here evaluated at x.
Where did that?
That
Oh,
was from the
oh.
fundamental. Let me get this. Okay. So what's one way of looking at this then? So this expression here. What is that? Remember, this is going to be, if you were to write this whole thing out. This expression here is partial b with respect to x, I hat plus partial b with respect to y, j hat plus partial b with respect to z, k hat. Okay, what would it be then? This is just the generalization of this to 3 dimensions.
yeah.
Okay, you can see that this piece is basically the 3-dimensional version of this. So this is really just 3-dimensional generalization of this EX minus dx. That's all that is. Now, does that make sense?
Yeah.
Okay. Warm up number 2. I want to talk about total differentials. Now, this is going to lead to the actual real derivation of this. Okay, so recall in 1D. If I have a function here like this, okay, that I can say this is approximately what? So let's actually draw a little graph.
Delta f over delta x.
This is x. This is f. Here's the function. Here's x like this. What is this guy here? This is the.
Looks like 2D though.
Oh, this is one thing. This is function of x.
Oh, okay. Okay, got it.
So what is this? Derivative is always what? The tangent of the.
Okay, curve.
Okay, the slope at this point here. So I can draw my little slope like this. So this right here, this is my slope. Here's this, yeah. What can I do with over here? I can call this point here x plus delta x. Okay. So here's my delta x. From right here, that spot right there would be what?
Which
From
spot?
here to there.
That would be delta f.
That would be my delta f, which is going to be your f of x plus delta x, and it's your f of x. Okay, so this is my delta f. Okay. So how does this difference here? So this slope here is really this distance here over this distance. Well, how does that compare to this distance over that?
It's almost.
Yeah, this is approximately equal to this delta f delta x. Right? So I can say that the change in f is approximately equal to the f dx dx. Does that make sense? Okay. Now let's generalize this.
Shouldn't it be delta x though? df
Oh,
dx
yes,
delta.
sorry. Okay. I took this over here, I made it a D. I have no idea why, because I'm being stupid. Call me out when I'm being stupid. So in 3D. So I have a function here of x, y, and z. I can say the partial of f with respect to x. Okay, what does that mean again? If I take the partial of f with respect to x?
You take a derivative with respect to x, everything else is constant.
Yeah, you take that, you're seeing how this function changes if you only change x. You're keeping y and z the same. I can say this is approximately equal to the change in f if you only change x over the change in x.
Hold on a second. Yeah, okay, got it.
Okay, so your change in f if you only change x is approximately partial of f with respect to x. Helps x.
Yep.
Well, what's going to be then the change in f if we only change y?
Pretty much the same thing where we just use y.
So likewise, we have that the change in f if you only change y is approximately the partial of f with respect to y, delta y, and the partial of f with respect to z is approximately this. For those of you who are engineers, taking an exact differential of something, especially when you're in thermodynamics, if you have no clue what to do, take an exact differential, you're probably right. Okay. So if I want the total change here, in other words, if I change x, y, and z at the same time, what would this approximately equal?
You would add them up, right?
You would add these up. I'd say it would be the approximate change in f if I only change x, plus the approximate change in f if I only change y, plus the approximate change in f if I only change z. So I can put this all in here. This is this guy here. Okay. And for those of you taking, if you take up upper level chemistry too, like PChem, you're going to do this all the time too. Okay.
Is that like the?
Physical chemistry.
Is it all chemistry? Physical chemistry?
Meaning it's going to be more like the physics of chemistry. You look at more, they do some quantum stuff and stuff like that. They do, I'd argue they do basic quantum, but that's, you know. But I mean, it's just, they do what they need. Okay. Now, this looks like something. What does this smell like?
Similar to our equation for gradient. The correct definition of a gradient.
Okay, we have an x thingy times an x thingy plus a y thingy times a y thingy plus a z thingy times a z thingy.
How about we replace it with IJK?
Keep going. Smells.
Spirit.
No, it's 7, okay? Then you have to have like incoherent words that don't really. Like
Okay.
this in your words, okay? That almost makes sense. Okay, so smells like a dot product, Reggie. Dot product. Dot product.
Okay.
Rough product, not rock product. Come on, get your Scooby Doo. So recall A dot B. How do we write A dot B? AX
X, VX,
BX plus
you go on.
AY BY plus AZ BZ. So basically X times an X plus a Y times a Y plus a Z times a Z. x times an x plus a z, y times a y plus a z times a z. Kind of smells dot product. So I'm going to put it in a dot product form. So I'm going to say that this approximately equal to this partial of f with respect to x, y hat, plus partial of f with respect to y, j hat, plus partial of f with respect to z, k hat. All this dotted into
XI hat plus Y hat plus
delta x
J
hat,
Yeah.
delta y j hat, it's delta z. Now, what would this be? Small change in x plus a small change in y plus a small change in z. This is what we call kind of this delta L vector. Okay. I'm going to define this quantity here, meaning 3 lines definition. I'm going to define this to be the gradient of f. So I can say that this partial of f with respect to this change in f total is approximately this delta f. And if I let these the delta L go to 0, then this actually then gives me this differential here. And it drops the.
What is in front of that L? Was that in it?
Oh, there should be enough here. Go ahead.
I was thinking up there on the top right when you did the bracket. That's a change.
That's a
This
delta.
this right, 3 lines.
The one to the right.
Right?
This guy here,
No.
That, but on the other side.
this guy.
Move to the right 3 times. One,
Keep moving your
2,
finger. Yep, one more.
No,
Here?
focus
Yep,
right.
that.
That's it. Change now.
Okay.
And all it is you can think of this gradient as being the 3-dimensional generalization of a derivative. There's more to it than that, but that'll work. Okay. Okay. This is called, when you do this here, this guy right here, this is called the exact differential. And if you do anything in engineering, especially thermodynamics, you're going to be taking exact differentials of everything. If you take PChem, especially the thermodynamics part of PChem, you're going to be taking exact differentials of everything. And you get a lot of math out of that. Okay, now let's apply to our case. We're going to apply this out to electrostatics. Okay. So we have this voltage here, and this voltage here is a function of x, y, and z. So if I want then this change in voltage here, the total change in voltage, if I change x, y, and z, what can I say this is approximately?
Delta L.
Okay. So what is that going to become?
Delta XI hat plus delta Y J
Yeah,
hat.
that'll be like, I'm gonna put them on with this. That'll be the size. So this is how much the voltage changes if we only change x. This is how much the voltage changes if we only change y. This is how much the voltage changes if we only change z. We know from what we said over here that this whole thing here, I can write it as the gradient of your voltage dotted into your delta L. Okay. How's almost over? Okay. Hell's almost over. And a professor always said that. He lied. Okay, so, okay. So now let's integrate that guy. From some initial to final spot. Okay. What would this give me? What's the integral of dv? V. And if I'm evaluating this is some initial final spot. So this V final minus V initial. Does that have a name?
Voltage difference.
That's your voltage difference. That's going to be this guy here. But do we have another way of writing the voltage difference?
Yeah, negative integral of E times dl. Oh my god. That's not crazy. Where's the proof?
No, we're going to have Shazam. Uh-oh. Shazam. Yeah, Shazam. Okay. Now what? We compare these two. So this guy here must be this guy here. Boom.
The first question was, how do we know it's the same DL, but it's just the change in direction that we're following, which is DL for that same thing.
Okay, that's kind of advanced. Okay, but I want you to see where it comes from. I'm not gonna, you won't have to do, there'll only be like 4 proofs on the next, on test 2, like a little bit harder than that. No,
Not too
you're not gonna be held responsible for this. But I did want you to see where it comes from. Okay? But this is a little bit on the advanced side. So if you look at this and went,
I think it's pretty straightforward.
well, I mean, if you've seen some of the stuff before, if not, it's not really. Okay. I think if I were an undergraduate seeing it for the first time, it's like, what happened to my little class? Okay. Okay, to actually use this is actually really simple. And let's actually see how we use it. I'm not gonna hold you responsible for the derivation. Or I'm saying that now. No, I'm not. Take the upper level courses and I do hold you responsible for derivations, but not here. Okay.
So do you like want us to take these up on courses? Because you keep telling us all this stuff.
Well, I do want you to take it. Okay?
You're scared.
One of those, I think some people, you either like this stuff or you don't. But that's not quite true. I think it's kind of, I think some people get intrigued by it. Other people, I always had to know where things come from, but I didn't know where something came from. I couldn't use it as an undergraduate. Like, where the hell did
This is
come from?
me. This is literally like, I
Okay.
can't.
It's like, what's the assumption here? Because I had some people, professors show me where things came from. It's like, I don't know what to do. I could not do those courses. Okay. Okay, let's do an example of this. Hey, we had the V of the disk. Okay, I don't remember what this is, but I think it's 2 pi k sigma square root of r squared plus g squared minus 1.
Minus Z.
Minus. Is that right?
Yeah, I think so.
Okay. I want you to find the disk.
Oh, that's.
Okay, what is the claim? The claim is it's going to be this. And what's our gradient operator equal to? I have partial here, V of the disk. J half. Partial V of this. Y plus partial V with respect to Z. J half. Now, what is the X dependence in this term here? 0. There is no X dependence. So you take the partial V with respect to X, what do you get? 0.
Wait, hold on. Go over it again.
Okay, is there any X dependence in there?
Oh. No.
Okay.
Okay.
Okay. So you take the partial of this with respect to X, you get 0. What's the Y dependence on this? 0. 0. So you take the partial of this with respect to Y, you get 0. So you only get this from here. So the whole expression reduces to 0. Sorry for going and drop light. This is minus k hat. Okay, all these are constants, so I can pull these out through the derivative. Of this k here, it's not that k there. Okay, what is the partial of this with respect to z? If this is the same thing as the 1/2.
Yeah, 1/2.
That gives me 1/2.
R squared.
This whole thing here to the minus 1/4 times
2z.
times 2z. Okay, then my body here, 1. So this tells me, okay, minus k hat, 2 pi k sigma. 2's go out, this gives me z over r squared plus z squared square root. 1. Shazam.
Should we get rid of the minus?
I would. I would never write it like this. I never like an expression starting with a minus sign. So I rewrite it with just rooting through the minus sign, but I'll do it like that. This is okay. So now we have 3 ways to find the electric field. What are the first 2 ways you're gonna have on your exam? Shooting has a collection of point charges. Gauss's law. Okay, so that's on the first test. On the second test, we'll then have 3 ways to find the electric field. What would they be?
First 2 plus this one.
First 2 plus this one, meaning you find the voltage first, treating it as a collection of little point charges. And then you use negative gradient to then find the electric field. So now we now have 3 ways to find the electric field. Okay? Have a great weekend. Oh, okay.
Yeah, we're trying.
It's just kind of brain damage.
Yeah, I think I needed that.
I have a test now.
Betty.
Thank you.
Betty.